Somewhere out there in the vast emptiness of space, invisible bullets are racing through the cosmos at nearly the speed of light particles, so energetic they could punch straight through solid lead without slowing down. These aren't fragments of distant stars or echoes of the Big Bang, they're cosmic rays, nature's own particle accelerators, hurling matter across the universe with forces we can barely comprehend. And they're not alone. All around us right this second, high-energy particles are raining down on Earth from sources we're still struggling to understand. Some carry energies millions of times stronger than anything our most powerful machines can create. Where do they come from? What accelerates them to such impossible speeds? And what secrets do they hold about the most violent corners of the universe? The story of these particles isn't just about physics, it's a cosmic detective story spanning over a century. Imagine a single subatomic particle, smaller than an atom, carrying enough energy to knock a baseball into orbit. That's not science fiction, it's real, and it's happening right now. These particles have traveled across galaxies, passing through stars and magnetic fields, only to end their journey in the palm of your hand if you know how to look. They've baffled scientists, rewritten the rules of physics, and even played unexpected roles in history, from unexplained glitches in early computers to radiation risks for astronauts. And yet, despite decades of study, they remain one of the universe's most tantalizing mysteries. So today, we're diving deep into the invisible storm of high-energy particles that surrounds us. From cosmic rays born in the wreckage of supernovas to neutrinos that pass through entire planets like ghosts, we'll uncover 30 astonishing facts about these cosmic speedsters. You'll learn how a single particle can outshine the energy of a professional baseball pitch, why some of them shouldn't exist according to our current physics, and how scientists are using them to peer into black holes and supernovas millions of light years away. This isn't just a journey through space, it's a trip to the very edge of what we know about the universe's most extreme forces, ready to have your mind blown. Let's begin. Here's one of the universe's great misnomers: cosmic rays aren't rays at all. They're not beams of light or electromagnetic waves like gamma rays or X-rays. Instead, picture tiny bullets of matter, subatomic particles hurtling through space at nearly the speed of light. The vast majority of these cosmic visitors are protons, the same positively charged particles found in the heart of every atom. But unlike the orderly protons in your body, these have been catapulted across galaxies with energies so colossal they make our most powerful particle accelerators look like toys. Their origins read like a catalogue of cosmic violence. When a massive star explodes as a supernova, the shockwaves can fling these particles across space like a celestial slingshot. Active galactic nuclei, the monstrous engines powered by supermassive black holes, launch them with forces we can barely comprehend. Even collisions between galaxies might serve as cosmic pinball machines, sending particles ricocheting through the void. These aren't gentle whispers from the universe, they're the screaming remnants of its most cataclysmic events. What's truly staggering is their journey. Some of these particles have traveled for millions of years, weaving through magnetic fields that twist their paths into impossible knots. They've dodged stars, slipped through gas clouds, and endured forces that would tear ordinary matter apart. And when they finally reach Earth, they don't stop politely at the atmosphere. They collide with air molecules in a spectacular burst of secondary particles, creating invisible fireworks that rain down on us every second. Yet for all their power, detecting them directly is like trying to catch a bullet with a butterfly net. Scientists use vast arrays of detectors spread across mountains or buried deep underground, waiting for the telltale signs of these high-speed interlopers. Some experiments even repurpose ancient Roman lead once used in aqueducts to shield their instruments from ordinary radiation, creating a silent vigil for the universe's most energetic messengers. The most jaw-dropping cosmic ray ever detected earned a name straight out of a comic book, the Oh My God particle. Picture this: on the 15th of October 1991, a solitary proton slammed into Earth's atmosphere over Utah, carrying more energy than a baseball hurled at 100 kilometers per hour. That's a subatomic particle with the kinetic punch of a professional athlete's fastball. To put it in perspective, this single proton packed 40 million times the energy of particles accelerated in the Large Hadron Collider, our most powerful human-made machine. Scientists calculating its speed found it was moving so close to light speed that in a race across our entire galaxy, it would beat a beam of light by less than a centimeter. That's how narrowly physics allows anything to approach the universe's ultimate speed limit. This discovery shattered expectations. According to our best theories, particles from distant galaxies should lose energy as they travel, scattered and slowed by the cosmic microwave background, the faint afterglow of the Big Bang. The Oh My God particle defied that logic. It arrived with so much energy that physicists still debate what cosmic catastrophe could have launched it. Was it a supermassive black hole's jet, a collision of dark matter, or something we haven't even imagined yet? Theories abound, but one thing's certain: this particle exposed gaps in our understanding of how the universe accelerates matter. Its detection was equally mind-bending. The Fly's Eye Observatory in Utah didn't catch the particle directly. Instead, it spotted the ultraviolet glow from the explosive cascade of secondary particles created when the proton struck air molecules. Imagine tracking a bullet by observing the splinters it creates upon impact. That indirect method revealed an energy so extreme that researchers reportedly checked and rechecked their calculations, convinced there must be an error. When the numbers held, the only appropriate reaction was the nickname that stuck. The Oh My God particle isn't just a record holder, it's a cosmic mystery that challenges the boundaries of physics. If such particles are common, they might reveal hidden forces or exotic objects lurking in deep space. Yet decades later, we've detected only a handful of similar ultra-high-energy cosmic rays, each one raising more questions than answers. They hint at a universe far more violent and unpredictable than our textbooks describe, where particles become celestial cannonballs, and the rules we know might just be the tip of the iceberg. These cosmic speed demons don't just move fast, they flirt with the universe's ultimate speed limit. Clocking in at just a hair's breadth below light speed, cosmic rays travel so rapidly that if you could race one from the moon to Earth, it would beat a photon by less than the width of a human hair. That tiny gap isn't because space holds them back. It's physics itself putting on the brakes. Einstein's theory of relativity dictates that nothing with mass can ever quite reach light speed, no matter how much energy you pump into it. But cosmic rays come staggeringly close, often hitting 99.9% of that limit. What's wild is how nature accomplishes what our most advanced machines cannot. The Large Hadron Collider, a 27-kilometer underground ring, needs colossal electromagnetic fields to accelerate particles to a fraction of cosmic rays' energy. Yet somewhere in deep space, natural processes launch protons and atomic nuclei to these extreme velocities effortlessly. Theories suggest shockwaves from supernovas act like cosmic particle surfboards, with magnetic fields repeatedly flinging particles back through the wavefront until they've built up ludicrous speed. Active galactic nuclei, supermassive black holes devouring matter, may whip particles outward in jets stretching thousands of light years like a cosmic slingshot. Detecting these near-light-speed projectiles is like trying to photograph a bullet with a disposable camera. Their velocity means they rarely stick around long enough to study directly. Instead, scientists rely on secondary clues, the particle shrapnel created when they collide with Earth's atmosphere. Some experiments use tanks of ultra-pure water or layers of specialized gel, waiting for the faint blue glow of Cherenkov radiation, the optical equivalent of a sonic boom, created when particles outpace light speed in that medium. Others deploy vast grids of sensors across deserts, capturing the cascades of debris from these high-speed impacts. But here's the cosmic irony. The faster these particles travel, the harder they are to trace back to their origins. At these velocities, even weak galactic magnetic fields, which permeate every corner of space, can bend their paths into pretzels. A proton arriving from the Andromeda galaxy might weave through interstellar space for millions of years, its trajectory scrambled beyond recognition. It's like trying to track a ricocheting bullet in complete darkness. This lost in transit effect means that even when we catch an ultra-high-energy cosmic ray, its birthplace often remains a mystery, leaving scientists to piece together cosmic crime scenes with half the evidence missing. Yet this speed also holds clues to the universe's most violent events. The energy required to accelerate particles this fast likely comes from environments where spacetime itself gets warped, near neutron stars, merging black holes, or regions of space where dark matter might be annihilating itself. Every near-light-speed particle is a postcard from places where physics operates at its most extreme, written in a language we're still learning to decode. And as astronomers combine cosmic ray data with gravitational wave and neutrino observations, we're starting to see the universe's most energetic phenomena in startling new dimensions. That invisible rain of cosmic particles isn't just a scientific curiosity, it's a silent saboteur wreaking havoc on our technology. Every second, high-energy protons and atomic nuclei slam into satellites, spacecraft, and even computers on Earth's surface, causing glitches that range from puzzling to catastrophic. These aren't science fiction scenarios, they're documented events with real-world consequences. When a cosmic ray strikes a microchip, it can flip individual bits of data from 0 to 1 or vice versa, like an invisible finger tapping the wrong key on a cosmic keyboard. Take the case of a commercial airliner cruising at high altitude. In 2008, a Qantas flight from Singapore to Perth suddenly plunged 200 meters in seconds, injuring passengers and crew. The culprit, a single cosmic ray striking an altitude sensor's computer chip, creating a false reading that triggered the autopilot to dive. Or consider the famous 1996 software bug that nearly derailed the Ariane 5 rocket's maiden flight. Researchers later traced similar errors to cosmic ray interference with onboard electronics. These particles don't discriminate between million-dollar satellites and your smartphone. The problem stems from how modern electronics work. As transistors shrink to nanometer scales, they become vulnerable to even tiny bursts of energy. When a high-speed cosmic particle barrels through a silicon chip, it leaves behind a trail of charged particles like microscopic lightning. This can scramble memory cells or even permanently damage circuits. Spacecraft face the greatest risk, lacking Earth's protective atmosphere to absorb incoming particles. The Hubble Space Telescope, for instance, routinely experiences up to 5 single-event upsets per day, momentary data corruptions caused by cosmic rays punching through its systems. Engineers have developed ingenious countermeasures. Mission-critical systems often use radiation-hardened chips with special shielding or error-correcting codes that automatically detect and fix flipped bits. Some satellites employ triple modular redundancy, running 3 identical systems simultaneously and voting on the correct output, assuming cosmic rays won't strike all 3 at once. Even consumer devices aren't immune. Researchers found cosmic rays caused roughly 1 unexplained crash per month in a sample of 1,500 Apple MacBooks. Perhaps most astonishing is how these particles reach ground-level electronics. While the atmosphere stops most cosmic rays, the resulting particle showers include neutrons that penetrate buildings and underground server farms. In 2003, a voting machine in Belgium mysteriously added 4,000 extra votes later attributed to a cosmic ray strike. Financial institutions now monitor for these soft errors that could potentially alter stock trades or bank balances. As our world becomes more interconnected and reliant on ultra-precise electronics, This invisible interference from space reminds us that we're all participants in a cosmic shooting gallery, where the bullets are subatomic and the targets are the very devices that power modern life. This ongoing battle between human technology and nature's particle accelerators has spawned an entire field called radiation effects engineering. From designing chips that can shrug off these energetic intruders to developing algorithms that can detect and correct their mischief, scientists are constantly innovating to keep our digital world running smoothly. Yet for all our safeguards, cosmic rays continue to expose the fragile boundary between our technological mastery and the universe's raw power, one bit flip at a time. For decades, scientists assumed the highest energy cosmic rays were born within our galaxy, perhaps flung outward by supernova explosions or the turbulent chaos around our Milky Way's central black hole. Then came the evidence that turned that assumption on its head: particles carrying energy so immense they couldn't possibly originate from local sources. Tracking their paths led researchers to a startling realization: the universe's most powerful particle accelerators lie far beyond our galactic neighborhood. The smoking gun emerged from meticulous observations of ultra-high-energy cosmic rays, those rare, jaw-dropping particles carrying energies exceeding 1 exaelectronvolt, roughly the kinetic energy of a mosquito in flight packed into a single proton. When scientists mapped their arrival directions, something peculiar stood out. They weren't clustered along the Milky Way's disk where most galactic matter resides. Instead, they appeared to come from all directions with no preference for our galaxy's structure. This isotropic distribution was the first clue that their origins weren't local. If these particles were galactic, their paths would have been twisted by our galaxy's magnetic field into recognizable patterns, like iron filings aligning around a magnet. Their randomness pointed to forces unshackled from our cosmic backyard. Then came the physics-based knockout punch. At these extreme energies, cosmic rays should interact with the cosmic microwave background, the faint afterglow of the Big Bang, losing energy over long distances like a marathon runner hitting a wall. This phenomenon, called the Greisen-Zatsepin-Kuzmin cutoff, predicts that no proton should retain such staggering energy if it travels more than 50 million parsecs. And yet, we detect them. The only explanation: these particles must originate from relatively nearby in cosmic terms within our local supercluster of galaxies, but decisively outside the Milky Way. The prime suspects: active galactic nuclei, the luminous hearts of distant galaxies powered by supermassive black holes. As these black holes devour surrounding matter, they spew out jets of plasma stretching millions of light years, acting as natural particle accelerators of unimaginable scale. Simulations show magnetic fields in these jets can slingshot protons to energies 100 million times greater than the Large Hadron Collider. Other likely sources include galaxy collisions, cosmic pile-ups where shockwaves accelerate particles to extreme velocities, or perhaps even more exotic phenomena like decaying superstrings or dark matter annihilation. But the real detective work lies in connecting individual particles to their birthplaces, a challenge akin to tracing a single raindrop back to a specific cloud in a hurricane. While lower-energy cosmic rays might spiral through galactic magnetic fields for millennia, ultra-high-energy particles travel so fast that their paths bend only slightly, preserving some directional clues. The Pierre Auger Observatory, a sprawling detector array in Argentina, has recorded tantalizing correlations between these particles and nearby active galaxies like Centaurus A, though the data remains frustratingly sparse. This extragalactic origin story reshapes our understanding of the universe's most energetic processes. It means the particles striking Earth carry fingerprints from galaxies millions of light years away, offering a unique probe into environments we could never otherwise study. Each ultra-high-energy cosmic ray is a messenger from realms where gravity twists spacetime into knots and magnetic fields dwarf anything in our experience, a tiny piece of distant cosmic violence delivered to our doorstep at nearly the speed of light. The universe's most energetic particles shouldn't exist, at least not according to conventional physics. The sheer violence required to accelerate a single proton to energies rivaling a major league fastball defies intuition. Yet cosmic rays routinely shatter these energy barriers, leaving scientists scrambling to explain the cosmic engines capable of such extreme feats. The leading theory, Fermi acceleration, reads like something out of a high-stakes pinball tournament. Instead of flippers and bumpers, imagine shockwaves from supernova explosions acting as cosmic accelerators. When a star dies in a cataclysmic blast, it sends out ripples of charged gas at thousands of kilometers per second. Particles caught in these turbulent waves don't just ride them, they get ping-ponged back and forth across the shock front, gaining a little energy with each cosmic bounce. Over centuries, what began as a sluggish proton transforms into a high-speed bullet, ejected into space with enough force to pierce galaxies. But Fermi acceleration alone can't explain the universe's most extreme cosmic rays. The oh my god particle and its ultra-high energy cousins carry millions of times more energy than even supernovas can typically produce. This discrepancy has physicists probing more exotic explanations. Some point to active galactic nuclei, where supermassive black holes generate magnetic fields trillions of times stronger than Earth's. In these cosmic maelstroms, particles could surf along rotating magnetic field lines, spiraling outward like beads on a twirling string until they reach unimaginable speeds. Others speculate about colliding galaxy clusters, vast mergers where entire galaxies smash together, creating shock waves spanning millions of light years. These cosmic pileups might act like natural particle colliders, dwarfing anything humans could build. The puzzle deepens when you consider how efficiently these accelerators operate. Human-made particle colliders like the Large Hadron Collider require kilometers of precision engineering to reach a fraction of cosmic rays' energy. Yet nature achieves far greater results with no visible infrastructure, just raw gravitational and electromagnetic forces sculpted by chaos. Some theorize that certain cosmic accelerators exploit a phenomenon called magnetic reconnection, where tangled magnetic fields suddenly snap and recombine, releasing bursts of energy that can slingshot particles to relativistic speeds in milliseconds. It's the difference between a gradual uphill climb and being catapulted by an invisible cosmic hand. What makes this mystery so thorny is the lack of direct evidence. Unlike telescopes that can image distant galaxies, cosmic ray detectors only catch the aftermath, the scattered clues of particles that have traveled for eons. Their paths twisted by galactic magnetic fields, these messengers arrive at Earth stripped of most directional information about their origins. It's like trying to reconstruct a hurricane by studying individual raindrops. New observatories are attempting to solve this by combining multiple detection methods, tracking not just the particles themselves, but the faint glow of ultraviolet light they produce in the atmosphere or the radio pulses generated by their collisions. The implications stretch beyond astrophysics. If we could decode nature's acceleration recipes, we might revolutionize energy science or space travel. Imagine spacecraft propelled by miniature versions of cosmic shockwaves, or medical therapies that harness natural particle beams. For now, these cosmic accelerators remain both a testament to the universe's unfathomable power and a humbling reminder of how much we have yet to learn. Each ultra-high-energy particle carries encrypted instructions from the cosmos' most extreme environments. If only we could crack the code. Could cosmic rays be secretly pulling Earth's climate strings? It's one of the most hotly debated ideas in atmospheric science. The possibility that these high-energy particles from deep space might influence cloud formation, potentially altering global temperatures. This theory hinges on an invisible chain reaction that begins when a cosmic ray slams into our atmosphere. the collision creates a cascade of secondary particles, some carrying just enough energy to ionize molecules in the air, essentially knocking electrons loose and creating charged pathways where none existed before. Here's where it gets controversial. Laboratory experiments have shown that these ionized pathways can act as seeds for aerosol clusters, microscopic specks around which water vapor condenses. More aerosols mean more potential cloud droplets, and over time, these droplets might grow into full-fledged clouds. If the theory holds, spikes in cosmic ray activity could lead to increased cloud cover, especially low-altitude cumulus clouds that reflect sunlight back into space. The implication: cosmic rays might serve as a natural thermostat, cooling Earth when they're abundant and allowing warming when they're scarce. The Sun plays a surprising role in this cosmic climate dance. During periods of high solar activity, our star's strengthened magnetic field acts like a shield, deflecting low-energy cosmic rays away from Earth. Historical climate data reveals curious correlations like the 17th century Maunder minimum, when both sunspot activity and cosmic ray flux reached extremes. Temperatures during this period dropped so dramatically that London's Thames River regularly froze over, a phenomenon immortalized in winter festival paintings. Could diminished solar shielding and increased cosmic ray bombardment have contributed to this little ice age? Proponents of the cosmic ray climate link argue the timing is more than coincidence. Yet the scientific community remains sharply divided. Critics point out that while lab experiments demonstrate cosmic rays can generate aerosols, the leap to large-scale climate effects lacks conclusive evidence. Cloud formation depends on countless variables: humidity, temperature, existing particulate pollution, making it difficult to isolate cosmic rays as a primary driver. Satellite data has produced conflicting results, with some studies showing slight cloud cover variations tied to cosmic ray fluctuations and others finding no meaningful connection. The European Organization for Nuclear Research even built a cloud chamber called CLOUD at their Geneva facility to test the theory under controlled conditions, revealing that while cosmic rays do enhance aerosol formation, their overall climate impact appears modest compared to human-caused greenhouse gas emissions. What makes this debate so electrifying is its potential to rewrite our understanding of climate drivers. If cosmic rays significantly influence cloud cover, it would add a new variable to climate models, one tied to galactic forces beyond our solar system. It might also help explain puzzling climate shifts in Earth's distant past, like sudden warming or cooling events that lack obvious terrestrial triggers. But for now, the theory remains in limbo, caught between tantalizing possibilities and insufficient proof. As researchers refine detection methods and climate models grow more sophisticated, we may finally get answers about whether the universe's most energetic particles are quietly shaping Earth's sky, one ionized molecule at a time. Up in the thin air of the stratosphere, suspended beneath a hydrogen-filled balloon, an Austrian physicist named Victor Hess made a discovery that would rewrite our understanding of the universe. It was 1912, and scientists were puzzled by strange radiation that seemed to come from everywhere, even underground. Most assumed it originated from Earth itself, perhaps seeping up from radioactive rocks in the crust. But Hess had a hunch the truth lay far above. On a daring series of balloon flights, some reaching altitudes over 5,000 meters without oxygen equipment, Hess carried electroscopes, simple devices that measured radiation by how quickly charged gold leaves collapsed. What he found defied all expectations. Instead of decreasing with height, the radiation intensified dramatically, nearly tripling at the highest altitudes. This wasn't earthly radiation at all. Hess had stumbled upon something entirely new, a shower of energetic particles pouring down from space. His pioneering flights earned him the Nobel Prize and gave cosmic rays their name, though we now know they're particles, not rays. The risks Hess took were staggering. Early 20th century balloon technology offered little protection against the freezing cold or thin air. During one ascent, Hess passed out from hypoxia, only regaining consciousness as his balloon descended through thicker atmosphere. Yet he pressed on, conducting multiple flights by day and night to rule out solar influence. The data was incontrovertible. This mysterious radiation increased with altitude regardless of time or weather, proving its extraterrestrial origin. Hess's discovery opened a window into the cosmos that we're still peering through today. Those simple gold leaf electroscopes detected what we now understand as secondary particles, the debris from cosmic rays colliding with atmospheric atoms. His courage to venture where the air was too thin to breathe revealed that Earth is constantly bombarded by fragments of distant stellar explosions, a reality as astonishing today as it was over a century ago. Modern particle astrophysics owes its existence to a man willing to float into the unknown with little more than scientific curiosity and a balloon made of rubberized fabric. Every breath you take contains traces of cosmic history, not just oxygen and nitrogen, but atoms forged by interstellar particles slamming into our atmosphere. Among these cosmic byproducts is carbon-14, a rare isotope that revolutionized archaeology and changed how we measure time itself. This isn't some exotic material found only in labs, it's inside you right now, woven into your DNA, created by violent collisions between cosmic rays and the very air we breathe. Here's how this atomic alchemy works. When a high-energy cosmic ray, usually a proton, crashes into an atmospheric nitrogen atom, the impact shatters the nitrogen's nucleus, ejecting a neutron like a billiard ball. That loose neutron then collides with another nitrogen atom, transforming it into carbon-14 through a process called neutron activation. The result: an unstable isotope that behaves like ordinary carbon but carries a hidden clock in its nucleus. Over time, carbon-14 decays back into nitrogen at a predictable rate, with half of it vanishing every 5,730 years, a stopwatch that starts ticking the moment it forms. This delicate balance between creation and decay creates a cosmic equilibrium. Carbon-14 is constantly being produced in the upper atmosphere while simultaneously breaking down, maintaining a steady concentration in Earth's carbon cycle. Plants absorb it during photosynthesis, animals ingest it by eating those plants, and eventually it becomes part of every living creature. The real magic happens when an organism dies. At that moment, its carbon-14 supply stops replenishing, and the isotope begins its predictable decay. By measuring how much remains in ancient wood, bones, or cloth, scientists can calculate exactly how long ago that organism last drew breath, a technique called radiocarbon dating that transformed our understanding of human history. But cosmic rays don't just make carbon-14. They spawn a whole periodic table's worth of rare isotopes through similar reactions. Beryllium-10 forms when cosmic rays blast oxygen atoms apart, leaving behind a fingerprint in ice cores that reveals ancient solar activity. Chlorine-36 accumulates in rocks exposed at Earth's surface, helping geologists date landslides and glacier movements. These isotopes serve as invisible diaries, recording everything from supernova explosions to fluctuations in Earth's magnetic field. What's astonishing is the scale of this process. Each square meter of Earth's upper atmosphere produces about 20,000 carbon-14 atoms per second, enough to create roughly 8 grams of the isotope globally each year. That might sound insignificant, but over millennia it accumulates into a measurable record. Even more remarkably, this production rate isn't constant. When the sun's activity wanes during solar minimums, more cosmic rays penetrate our atmosphere, boosting isotope production. Massive stellar explosions within a few hundred light-years could theoretically double Earth's carbon-14 levels overnight, leaving spikes in tree rings that persist for centuries. This cosmic fingerprinting has upended historical timelines. When radiocarbon dating revealed that Egypt's Old Kingdom pyramids were centuries older than archaeologists believed, it rewrote chronologies across the ancient world. The technique exposed the Shroud of Turin as a medieval artifact, not a first-century relic, and verified the astonishing age of Ötzi the Iceman, a 5,000-year-old traveler preserved in alpine ice. Without cosmic rays constantly replenishing Earth's supply of these rare isotopes, we'd be blind to the true age of countless artifacts, forced to rely on guesswork and fragmented records. Yet this system isn't flawless. Cosmic ray flux varies with solar cycles and Earth's shifting magnetic field, requiring careful calibration using tree rings and ice cores. Nuclear testing in the 1950s and 60s flooded the atmosphere with artificial carbon-14, complicating modern measurements, and some materials, like marine shells, absorb carbon from sources with different isotope ratios, necessitating corrections. These challenges remind us that even the universe's most reliable clocks require meticulous interpretation. Beyond dating, these cosmic creations have surprising modern applications. Carbon-14 helps track illicit ivory by revealing when elephants were poached, traces the origins of counterfeit pharmaceuticals, and even monitors renewable biofuel content in gasoline. In particle physics, beryllium-10 serves as a cosmic ray meter, helping reconstruct past radiation levels. These isotopes, born from stellar violence and shaped by planetary chemistry, have become indispensable tools for understanding everything from climate history to black market networks. So the next time you look at an ancient artifact in a museum or check a carbon-neutral label, remember, you're witnessing the legacy of particles that crossed light years to etch their mark on our world. Cosmic rays don't just bring mysteries from deep space. They leave behind atomic breadcrumbs that help us unravel Earth's own story, one decaying nucleus at a time. Imagine floating in space, not the empty, silent void we often picture, but an invisible ocean of particles constantly swirling around you. This is the cosmic ray, see, an omnipresent bath of low-energy particles that fills every cubic centimeter of the universe. Unlike their ultra-high-energy cousins that make headlines, these background cosmic rays don't carry enough punch to light up detectors dramatically. Yet their sheer ubiquity makes them one of the cosmos' most fundamental features, a whispering hum underlying the universe's grand explosions and collisions. Most of these particles are protons, moving at about 80% the speed of light, still blisteringly fast by human standards, but downright leisurely compared to cosmic extremes. They originate from relatively tame sources, the steady simmer of solar wind from nearby stars, the fading shockwaves of ancient supernovas, or even the gentle leakage of particles trapped in our galaxy's magnetic fields. What's remarkable isn't their individual energy, it's their overwhelming numbers. Every second, about 5 of these particles pass through your thumbnail, whether you're on a mountaintop or deep underground. This perpetual drizzle shapes space in unexpected ways. Astronomers liken it to static on an old radio, a faint noise that obscures delicate signals from distant galaxies. Space telescopes must account for this background when studying faint objects, much like photographers adjust for light pollution. The cosmic ray even influences spacecraft design, as its cumulative effects can degrade solar panels and sensitive electronics over decades-long missions. Yet this ever-present radiation also carries hidden value. By studying subtle variations in the cosmic ray's intensity, scientists can map our solar system's journey through the Milky Way. As the Sun orbits the galactic center, it periodically passes through regions where interstellar gas clouds dampen these particles like a ship leaving wakes in an invisible ocean. These dips and surges create a fingerprint of our cosmic neighborhood structure. Perhaps most astonishing is how deeply these particles integrate with life on Earth. The carbon-14 in your bones, the mutations driving evolution's slow dance, all stem from this ceaseless particle rain. It's a reminder that the universe never rests, and even its quietest phenomena leave fingerprints on everything from DNA to deep space probes. Far from empty, the void between stars thrums with motion, a sea whose waves are particles and whose tides have shaped existence itself. The relentless barrage of cosmic rays doesn't stop at Earth's surface, it tunnels deep underground, reaching places no sunlight ever touches. When high-energy protons from space collide with atoms in our atmosphere, they spawn a cascade of secondary particles, including muons. These heavy cousins of electrons pack enough punch to slice through hundreds of meters of solid rock like a hot knife through butter. While most particles get absorbed within the first few meters, muons streak through entire mountains, leaving trails detectable in subterranean labs and even ancient tombs. Muons owe their penetrating power to two key traits, mass and velocity. Nearly 200 times heavier than electrons, they interact less with matter as they zip by at nearly light speed. Picture a freight train barreling through fog where tiny water droplets might slow a bicycle. The massive train plows through unaffected. This lets muons reach depths where other particles vanish, delivering cosmic signatures to places like the Gran Sasso Laboratory in Italy, buried under 1.4 kilometers of mountain. Scientists have turned this phenomenon into an ingenious imaging technique called muon tomography. Just as X-rays reveal bones beneath skin, naturally occurring muons map dense structures hidden underground. When archaeologists suspected a hidden chamber in Egypt's Great Pyramid, they placed muon detectors inside to track how many particles pass through different sections. Areas with fewer muons indicated thicker stone-like shadows in a cosmic spotlight. The method confirmed the existence of the pyramid's mysterious void in 2017, solving a 4,500-year-old architectural puzzle without moving a single stone. Beyond archaeology, this technology safeguards nuclear facilities. Unlike traditional scans that require intrusive equipment, muon tomography passively images radioactive materials through walls by measuring how muons scatter off dense uranium or plutonium cores. After the Fukushima disaster, researchers deployed muon detectors to peer inside damaged reactors, locating melted fuel without risking human exposure. Even volcanoes have come under muon surveillance stations placed around Mount Etna track particle fluxes to model magma movements, offering early warnings of potential eruptions. The real marvel is how these applications repurpose what was once considered background noise. Every square meter of Earth's surface gets hit by about 10,000 muons per minute, a number that drops but never zeroes out, even deep underground. By tuning into this constant cosmic drizzle, we've unlocked a non-invasive way to explore everything from ancient tombs to modern hazards, proving that sometimes the universe provides its own flashlight. Could the same particles that threaten astronauts and scramble computers have also sparked life itself? This provocative idea suggests cosmic rays, often seen as destructive forces, may have been unexpected midwives in life's birth on Earth. When high-energy protons from deep space collide with molecules in water or air, they don't just break things apart. They can forge entirely new chemical pathways. Laboratory experiments show these collisions generate reactive fragments that could have assembled into life's building blocks on early Earth, like a molecular puzzle shaken into place by cosmic interference. Take the mystery of chirality, the handedness found in biological molecules. All known life uses left-handed amino acids and right-handed sugars, a uniformity that defies random chemical processes. Some researchers propose polarized light from cosmic rays could have tipped the scales, selectively destroying one molecular orientation while leaving the other intact. It's as if the universe's particle storm acted as a cosmic filter, sieving randomness into the precise arrangement life required. These particles might have done more than shape molecules, they could have powered life's first engines. In hydrothermal vents or tidal pools, cosmic ray-induced ionization may have created electrochemical gradients similar to those modern cells use for energy. Picture a primordial pond repeatedly struck by particle showers. its waters crackling with temporary charge separations that accidentally jump-started proto-metabolic cycles. Even today, extremophiles thriving in radioactive environments hint at how early life might have harnessed such violent energy sources. The timing adds another layer of intrigue. 4 billion years ago, Earth's weaker magnetic field and thicker atmosphere created ideal conditions for cosmic rays to penetrate shallow waters where organic molecules concentrated. Unlike ultraviolet light, which gets absorbed at the surface, cosmic rays deliver energy bursts deep into liquid environments, potentially driving chemistry in places sunlight couldn't reach. Some models suggest particle showers could have boosted mutation rates in early replicators, accelerating evolution before DNA repair mechanisms existed. Yet this theory courts controversy. Critics argue that while cosmic rays can indeed alter chemistry, their destructive effects might outweigh any constructive role. The same particle strikes that potentially forged complex molecules could also have shredded delicate probiotic assemblies. It's a cosmic balancing act: too little radiation, and molecules lack the energy to overcome chemical barriers; too much, and any nascent structures get obliterated. What makes the hypothesis compelling is its testability. Scientists are replicating probiotic soups in particle accelerator beams, watching how amino acids behave under simulated cosmic ray bombardment. Others scour the genomes of radiation-resistant bacteria for molecular fossils, enzymes that might have evolved to harness or repair cosmic ray damage. Even meteorites bearing amino acids with the same chiral bias as Earth life hint at a universal bias imprinted by space radiation. Whether cosmic rays were midwives or merely bystanders in life's origins, their potential role reminds us that biology didn't evolve in isolation. From the molecular asymmetry in our cells to the energy pathways powering every organism, life's blueprints may carry fingerprints from the universe's most violent particle accelerators, written in chemistry we're only beginning to decode. To grasp the sheer violence behind ultra-high-energy cosmic rays, consider this: a single one of these particles carries more kinetic energy than a professional boxer's punch, all concentrated into a subatomic speck smaller than an atom. These aren't just remnants of cosmic accidents, they're the fingerprints of the most cataclysmic events since the universe began. When astronomers compare the energy scales, even the brightest supernovas and colliding neutron stars pale next to the forces needed to accelerate particles to such extremes. The numbers defy comprehension. The highest energy cosmic ray ever detected packed 50 joules of energy, enough to power a light bulb for a fraction of a second, all crammed into a proton traveling at 99.9999999% the speed of light. What cosmic phenomenon could unleash such fury? The leading suspects operate on scales that dwarf human imagination. Take tidal disruption events, when a star strays too close to a supermassive black hole and gets shredded into a spinning disk of plasma. The magnetic fields in these disks can act like cosmic railguns, launching particles with energies exceeding 100 exaelectron volts. Or consider blazars, distant galaxies with jets of plasma pointing directly at Earth, powered by black holes spinning at relativistic speeds. These jets might focus particles into narrow beams, like a celestial particle accelerator aimed straight at our planet. Yet even these titanic events struggle to explain the upper limits of cosmic ray energy. Some theories speculate about rarer, more exotic origins, colliding galaxy clusters generating shockwaves spanning millions of light-years, or perhaps the annihilation of hypothetical dark matter particles with masses far beyond anything we've detected. The most extreme proposals involve defects in spacetime itself, cosmic strings left over from the Big Bang snapping like rubber bands and releasing bursts of energy that make supernovas look like firecrackers. The temporal scale adds another layer of awe. Many of these particles have traveled for hundreds of millions of years, surviving a gauntlet of magnetic fields and interstellar gas that should have sapped their energy. That they arrive at Earth with such undiminished force suggests their birth events were even more violent than we've observed in the contemporary universe. It's as if we're receiving messages from an era when the cosmos operated under different rules, a time when collisions between primordial supermassive black holes or phase transitions in the early universe might have unleashed energies we can't replicate or even fully model with modern physics. What makes these particles so invaluable to science isn't just their energy, it's what they reveal about the universe's operating limits. Every time one strikes Earth's atmosphere, it's effectively conducting an experiment at energies far beyond what any human-built collider could achieve. The resulting particle showers recreate conditions not seen since the first seconds after the Big Bang, offering glimpses into how matter behaves under extremes we can't otherwise study. Some models suggest that at these energies, particles might interact differently with spacetime itself, potentially revealing cracks in Einstein's theory of relativity or evidence of extra dimensions. Yet for all their staggering power, these cosmic bullets remain frustratingly elusive. They arrive at Earth at a rate of about 1 per square kilometer per century, so rare that detectors must span entire countries to catch them reliably. The Pierre Auger Observatory in Argentina, covering 3,000 square kilometers, has recorded fewer than 30 of the very highest energy events since its inception. Each detection triggers a scramble to trace its path backward, but galactic magnetic fields twist these trajectories into indecipherable knots, leaving scientists to piece together cosmic crime scenes with only the faintest of clues. This combination of extreme energy and profound mystery makes ultra-high-energy cosmic rays one of physics' great frontier puzzles. They challenge our understanding of how the universe concentrates energy, how matter behaves at its limits, and what unknown forces might be lurking in the voids between galaxies. Every recorded event is a snapshot of physics pushed to its breaking point, a reminder that the cosmos harbors violence we've only begun to imagine. And with new observatories like the upgraded telescope array in Utah coming online, we might soon catch particles carrying even more impossible energies, rewriting the textbooks on what nature is capable of. One of the most baffling mysteries in astrophysics isn't some distant galactic phenomenon, it's happening right over our heads. Ultra-high-energy cosmic rays routinely smash through what should be an impenetrable cosmic speed limit, the Greisen-Zatsepin-Kuzmin cutoff. This theoretical barrier, predicted back in 1966, states that no proton should retain energies above about 5 times 10 to the 19th electron volts when traveling vast intergalactic distances. The reason: the universe itself should sap their energy long before they reach us. Yet detectors keep catching these rule-breaking particles, arriving with energies that make physicists double-check their instruments and rewrite their equations. The GZK cutoff isn't just some arbitrary line, it's woven into the fabric of space. As ultra-high-energy protons traverse the cosmos, they inevitably collide with photons from the cosmic microwave background, the afterglow of the Big Bang. These encounters should drain their energy through pion production, a process where protons lose momentum by creating new particles. Over distances beyond 50 megaparsecs, roughly 160 million light-years, this energy drain ought to render intergalactic protons harmless by the time they reach Earth. Think of it like a marathon runner trying to sprint through a vat of molasses. Eventually, even the strongest competitor would slow to a crawl. But cosmic rays laugh in the face of this cosmic drag. The Oh My God particle and others like it carry energies up to 300 times higher than the GZK cutoff allows. This presents only two possibilities. Either these particles didn't travel far, originating improbably close to Earth, or our understanding of high-energy physics contains fundamental gaps. The first option raises eyebrows because nothing in our local galactic neighborhood appears powerful enough to produce such extreme energies. The second possibility. That's where things get revolutionary. Some theorists suggest these particles might be signs of exotic new physics, perhaps evidence that Einstein's relativity breaks down at energies we've never before observed. Others propose they're not protons at all but heavier atomic nuclei like iron, which interact differently with the cosmic microwave background. More radical ideas invoke hypothetical particles like topological defects left over from the early universe, decaying after billions of years to release bursts of energy that mock conventional limits. There's even speculation that cosmic rays might occasionally cheat by transforming into different particle types mid-journey, bypassing energy loss mechanisms before reverting to their original form near Earth. The implications rattle the foundations of modern astrophysics. If the GZK cutoff is wrong or incomplete, it could mean our models of particle interactions at extreme energies need a complete overhaul. Laboratories like the Pierre Auger Observatory have spent decades collecting data to test these boundaries, only to find the universe keeps delivering surprises. Each ultra-high-energy cosmic ray that breaches the theoretical limit carries a coded message about physics operating in regimes we can't reproduce in any collider, under conditions that existed only in the universe's first moments. What makes this puzzle so tantalizing is its connection to cosmic censorship, the idea that the universe naturally hides its most violent secrets from view. The GZK cutoff was supposed to be one such censorship mechanism, preventing us from witnessing impossibly energetic events across vast distances. Yet these rogue particles slip through the cosmic net, offering fleeting glimpses of physics operating beyond our textbooks. Decoding their origins might require rewriting not just astrophysics textbooks, but our very understanding of how energy, matter, and spacetime interact at the extremes of existence. Until then, every detection remains both a triumph of observation and a humbling reminder of how much we have yet to learn. For decades, cosmic rays seem to arrive from everywhere and nowhere at once, their directions scrambled by galactic magnetic fields into an indistinguishable haze. Then astronomers noticed something peculiar: tiny excesses in certain patches of sky where these high-energy particles appeared slightly more often than random chance would predict. These cosmic hotspots might finally hold clues to the universe's most powerful accelerators, offering the first real chance to trace particles back to their violent birthplaces. One of the most tantalizing hotspots aligns roughly with a region near the constellation Ursa Major, where the Pierre Auger Observatory detected an unexpected clustering of ultra-high-energy cosmic rays. Unlike lower-energy particles whose paths get hopelessly tangled by magnetic fields, these extreme particles travel so fast that their trajectories bend only slightly, like bullets fired through a gentle breeze. Tracing their paths backward points toward potential sources less than 200 million light-years away, likely within our local supercluster of galaxies. The hotspot's rough position matches up with several active galactic nuclei, supermassive black holes devouring matter and spewing out particle jets with energies beyond human comprehension. Yet the plot thickens when comparing data from different observatories. The telescope array in Utah spotted its own hotspot in a different part of the sky, this one potentially linked to a supermassive black hole merger billions of years ago. These mismatches could mean the universe has multiple types of cosmic ray factories, each leaving distinct fingerprints, or they might reflect something stranger, perhaps particles scattering off invisible structures in intergalactic space, like a flashlight beam warped by a funhouse mirror. What makes these hotspots so valuable is their rarity. For every 100 cosmic rays arriving from random directions, maybe one or two trace back to these concentrated regions. Teasing out such subtle patterns requires detectors covering hundreds of square kilometers, recording particle showers for decades. The statistical confidence remains shaky, like trying to prove a rigged roulette wheel by spotting slight biases in a casino's nightly records. But as datasets grow, these faint cosmic whispers are getting louder. The emerging map challenges long-held assumptions. Many theorists expected cosmic rays to originate from nearby supernova remnants within our galaxy. Yet the hotspots point decidedly outward toward extragalactic monsters like Centaurus A, a turbulent galaxy 12 million light-years away with a black hole-driven jet visible in radio telescopes. Other candidate sources include starburst galaxies undergoing frenzied star formation, their collective supernova creating overlapping shock waves that could accelerate particles to unprecedented energies. Perhaps most intriguing are the blank spots regions where cosmic rays conspicuously avoid. Some align with the local void, a vast emptiness bordering our galactic neighborhood where few galaxies reside. These cosmic deserts might confirm that ultra-high-energy particles can't travel indefinitely. They lose steam crossing expanses where no powerful sources exist to replenish their numbers. It's as if the universe left us breadcrumbs in both presence and absence, mapping its high-energy geography through what arrives and what doesn't. Current observatories lack the resolution to pinpoint exact sources. Imagine trying to identify a specific streetlight in a blurred nighttime photo of a distant city. Next-generation detectors like the planned square-kilometer array radio telescope aim to change that, correlating cosmic ray arrivals with detailed maps of active galaxies and merger events. For now, these hotspots remain fuzzy signposts, hinting at a hidden network of cosmic accelerators whose full nature still eludes us. Every particle cluster we find is a potential thread in the tapestry, tugging us closer to understanding how the universe orchestrates its most spectacular particle physics experiments. One cosmic ray doesn't travel alone, it brings an entourage. When a single high-energy proton from deep space slams into Earth's atmosphere, it doesn't just stop politely at the doorstep. Instead, it triggers an avalanche of particles so vast it could outnumber the human population of a small country. This phenomenon, called an extensive air shower, turns one invisible cosmic bullet into a fireworks display of secondary particles spanning kilometers, all born from a single collision at the edge of space. The chain reaction starts 80 kilometers up, where the rarefied air barely slows the incoming particle. Striking a nitrogen or oxygen nucleus head-on, the cosmic ray shatters it like a cue ball breaking a rack in pool. But instead of scattering billiard balls, this impact sprays out pions, muons, electrons, and gamma rays, each carrying a fraction of the original energy. These newcomers then collide with other atoms, producing more particles in an exponential cascade. Within milliseconds, what began as one proton multiplies into billions of descendants, spreading outward in a conical shower that can blanket several square kilometers of Earth's surface. Detecting these showers requires clever engineering. Since the primary cosmic ray vanishes in the first collision, scientists piece together its properties by studying the secondary particles that survive the atmospheric gauntlet. Ground-based observatories use arrays of water tanks or scintillator detectors spread across vast areas, waiting for the synchronized flashes that signal a shower's arrival. Some particles, like muons, penetrate all the way to the surface, while others, such as electrons and positrons, get absorbed higher up. By triangulating the timing and density of these signals, researchers can reconstruct the original cosmic ray's energy and direction with astonishing precision. The sheer scale of these showers defies intuition. A single ultra-high-energy cosmic ray can produce a particle cascade containing more electrons than there are stars in the Milky Way, all from a collision involving a speck of matter too small to see. The most energetic showers even generate faint pulses of radio waves and ultraviolet light, visible as eerie glows to sensitive instruments. In fact, the first evidence of cosmic rays came not from direct detection, but from the ionization trails left by these atmospheric fireworks, a discovery that earned Victor Hess a Nobel Prize in the 1930s. What's truly remarkable is how nature's particle physics lab operates right above us. Every square kilometer of Earth's surface gets hit by about one of these extensive air showers per second, a constant, invisible drizzle of cosmic debris. Next time you feel a raindrop, consider this. Odds are, a particle from a dying star or a distant black hole just shattered an atom in the air above you, sparking a chain reaction that's been traveling across the cosmos for millions of years, only to end its journey as a whisper in our atmosphere. Nestled in Argentina's Pampas grasslands lies the world's most ambitious cosmic ray hunting ground, the Pierre Auger Observatory. This sprawling scientific installation covers 3,000 square kilometers, an area larger than some small countries, specifically designed to catch the universe's most elusive particles in the act. Unlike traditional telescopes that peer at distant stars, Auger's sensors stare straight up, waiting for the telltale signs of ultra-high-energy cosmic rays colliding with Earth's atmosphere. The scale is staggering: 1,600 water tank detectors spaced exactly 1.5 kilometers apart, each containing 12 tons of ultra-pure water, plus 24 fluorescence telescopes monitoring the night sky for faint ultraviolet flashes. Together, they form a hybrid detection system capable of capturing both the ground-level splash and the atmospheric glow of incoming particle showers. The observatory's design tackles cosmic rays' greatest detection challenges. When an ultra-high-energy particle hits the atmosphere, it creates an extensive air shower, a cascade of secondary particles spreading across dozens of square kilometers. Auger's water tanks act like cosmic puddles, waiting for these particles to strike. As charged particles zip through the purified water, they produce faint blue Cherenkov light, the optical equivalent of a sonic boom, which sensitive photomultiplier tubes at each tank's top detect with nanosecond precision. Meanwhile, the fluorescence telescopes capture the shower's ultraviolet glow as it develops through the atmosphere, like photographing the trail of a meteor in reverse. By combining both detection methods, scientists can triangulate a cosmic ray's energy, direction, and composition with unprecedented accuracy. What makes Auger truly revolutionary is its ability to catch the rarest cosmic rays, those with energies exceeding 100 exa-electronvolts. At these extreme levels, particles arrive at Earth only once per square kilometer per century, requiring an enormous net to catch them reliably. The observatory's South American location wasn't chosen by accident. Its flat terrain and clear skies provide ideal conditions, while the southern hemisphere's view includes the dense central region of our galaxy and nearby active galaxies like Centaurus A. Since operations began in 2004, Auger has detected hundreds of these ultra-high-energy events, each one a potential clue to cosmic accelerators we've yet to identify fully. The data has already upended expectations. Early results confirmed that the highest energy cosmic rays aren't protons as long assumed, but heavier atomic nuclei like nitrogen or iron, a finding that reshaped theories about their acceleration mechanisms. The observatory also discovered subtle anisotropies in cosmic ray arrival directions, faint hotspots suggesting some particles originate from nearby active galaxies rather than being uniformly distributed. Perhaps most importantly, Auger provided the first solid evidence that cosmic ray flux decreases above a certain energy threshold, a smoking gun for the long-predicted GZK cutoff, though a handful of particles still defy this limit. Maintaining this cutting-edge facility is a feat unto itself. Teams of technicians roam the grasslands in all weather, checking tanks for water purity. Even a few grams of salt contamination can ruin detection, and replacing photomultiplier tubes damaged by lightning strikes or curious wildlife. The data flows constantly to a central facility in Malagu, where physicists sift through petabytes of information, separating genuine cosmic ray events from false triggers like lightning or passing trucks. It's a 24-hour vigil for particles that may have traveled for millions of years, their journeys ending silently in the Argentine night. As Auger undergoes upgrades to improve its composition measuring capabilities, it remains humanity's best window into the ultra-high-energy universe. Every particle it catches carries encrypted information about the cosmos' most violent environments, black hole jets, galaxy collisions, or perhaps phenomena we haven't yet imagined. In the quiet expanse of the Pampas, under some of the clearest skies on Earth, science is piecing together a puzzle written in particles moving at nearly the speed of light, each one a messenger from realms where physics operates at its most extreme. Astronauts floating above Earth's protective atmosphere face an invisible threat far deadlier than vacuum or extreme temperatures, cosmic rays piercing their spacecraft like microscopic bullets. Unlike Earth's surface, where our planet's magnetic field and thick atmosphere absorb most space radiation, the International Space Station orbits in what amounts to a constant particle storm. A single day in space exposes astronauts to the equivalent radiation of 8 chest X-rays, while a 6-month stay equals lifetime occupational limits for nuclear workers. The danger escalates for missions beyond low Earth orbit. During the Apollo lunar flights, crews reported seeing flashes of light with closed eyes, later confirmed to be cosmic rays striking their retinas and triggering false visual signals in their optic nerves. These aren't just temporary annoyances. Studies of astronauts who spent months aboard the ISS show measurable DNA damage from cosmic ray exposure, with chromosome aberrations persisting years after returning to Earth. The real nightmare scenario emerges when considering long-duration missions to Mars, a 6-month journey through interplanetary space followed by months or years on the Martian surface could expose astronauts to radiation doses exceeding safe career limits by 4 to 5 times. Unlike Earth, Mars lacks a global magnetic field, and its thin atmosphere provides minimal shielding. NASA Curiosity rover measured surface radiation at about half the intensity of open space, enough to significantly increase cancer risks over extended stays. Space agencies are scrambling for solutions. The most straightforward approach, adding mass shielding, runs into practical limits. Aluminum spacecraft hulls actually make the problem worse by generating secondary radiation when cosmic rays collide with metal atoms. Scientists are experimenting with innovative materials like polyethylene, which contains abundant hydrogen atoms to absorb radiation without dangerous fragmentation, and even water-filled walls that double as radiation shields and water supplies. More exotic proposals include generating artificial magnetic fields around spacecraft, a scaled-down version of Earth's protective magnetosphere, or lining spacesuits with lightweight radiation-absorbing gels. The challenge intensifies when considering solar particle events, sudden bursts of radiation from the sun that can deliver lethal doses in hours. While these solar storms are easier to predict than cosmic rays, they require immediate protective measures. Future Mars habitats might include dedicated storm shelters with thick shielding where astronauts could wait out dangerous solar activity. Some designs incorporate regolith Martian soil as building material, piling it over habitats for natural radiation protection. NASA-planned Lunar Gateway Station will serve as a testbed for these technologies, monitoring radiation levels in cislunar space while evaluating new shielding materials. Perhaps most sobering is the biological dimension. Cosmic rays' high-energy ions can slice through cells like tiny wrecking balls, damaging DNA and increasing long-term cancer risks. Unlike gamma rays or X-rays that mostly cause localized damage, these heavy ion particles create dense trails of destruction through tissues. Studies using particle accelerators to simulate cosmic ray exposure show worrying neurological effects in mice, including cognitive decline and signs similar to early Alzheimer's. Protecting astronauts' bodies might require pharmacological interventions, drugs that boost DNA repair or flush out damaged cells before they turn cancerous. The cosmic ray dilemma represents one of the toughest hurdles for human space exploration. While we've developed workarounds for most other space hazards, from bone loss to muscle atrophy, radiation remains an unsolved problem with no perfect solution in sight. Every mission beyond Earth's protective bubble forces difficult trade-offs between safety, cost, and feasibility. As we prepare to send humans back to the Moon and onward to Mars, cosmic rays stand as silent guardians of the final frontier, reminding us that space remains fundamentally hostile to biological life, no matter how advanced our technology becomes. The collision of two neutron stars isn't just a spectacle of gravitational waves and gold production. It might also be one of the universe's most efficient cosmic ray factories. When these ultra-dense stellar corpses spiral into each other, the resulting merger unleashes energies that make hydrogen bombs look like firecrackers. Recent studies suggest the magnetic turbulence and shock waves from these events could accelerate particles to mind-bending speeds, potentially solving the mystery of how some cosmic rays reach such extreme energies. Picture the aftermath of a neutron star collision, a maelstrom where magnetic fields become so twisted they act like cosmic whipcracks, flinging protons and atomic nuclei outward at nearly light speed. Unlike supernovas, which generate chaotic, expanding shock waves, neutron star mergers create focused jets of plasma with magnetic fields trillions of times stronger than Earth. These conditions are perfect for a process called relativistic shock acceleration, where particles get repeatedly bounced back and forth across shock fronts, gaining energy with each pass like a pinball ricocheting between bumpers. Simulations show single protons could theoretically reach energies exceeding 100 exa-electronvolts in these environments, enough to explain even the most extreme cosmic rays we detect. The smoking gun might lie in multi-messenger astronomy, combining cosmic ray data with other cosmic signals. When detectors spotted gravitational waves from the historic neutron star merger GW170817 in 2017, astronomers scrambled to observe every wavelength from gamma rays to radio waves. Hidden in that data was a tantalizing clue: a brief but intense gamma ray burst followed by lingering X-ray emissions, signatures consistent with particle acceleration on an unimaginable scale. While no associated cosmic rays were definitively detected, the event was too far away for current observatories to pinpoint them. The energy profiles matched theoretical predictions perfectly. What makes neutron star mergers such compelling cosmic ray sources is their efficiency. These collisions concentrate more energy into a smaller volume than virtually any other phenomenon except black hole formation. The relativistic jets they produce aren't just powerful, they're narrowly focused, potentially funneling accelerated particles into tight beams that could traverse intergalactic space with minimal energy loss. It's the difference between a shotgun blast and a sniper rifle. Neutron star mergers might fire cosmic rays in precise directions rather than scattering them haphazardly, increasing the chances some would survive their journey to Earth intact. Yet mysteries remain. Neutron star mergers are relatively rare in our cosmic neighborhood, occurring maybe once per million years in a galaxy the size of the Milky Way. This scarcity raises questions about whether they could account for the steady flux of ultra-high-energy cosmic rays we observe. Some theorists propose these events might be disproportionately efficient producers, with each merger generating enough high-energy particles to compensate for their infrequency. Others suggest we might be seeing accumulated particles from numerous mergers over cosmic time, their combined output creating a background drizzle of extreme energy radiation. The next breakthrough could come from upgraded detectors like the planned square-kilometer array, which may spot telltale radio signatures of particle acceleration around distant mergers. Or perhaps future gravitational wave observatories will catch a nearby neutron star collision, allowing cosmic ray telescopes to hunt for associated particles in real time. Either way, these cosmic smash-ups are rewriting our understanding of how the universe's most energetic particles get their unbelievable speed, proving that sometimes the best cosmic accelerators aren't machines, but the violent dances of dead stars. Graph a cosmic ray's energy on a chart and you'll spot something bizarre. a sudden bend in the data around 1 billion electron volts, a feature so peculiar that scientists call it the ankle. This isn't just a minor statistical blip, it's a fundamental shift in the universe's particle distribution, marking where the rules of cosmic acceleration seem to change. Below this energy threshold, cosmic rays follow a predictable pattern. The higher the energy, the fewer particles we detect. But at the ankle, the trend abruptly flattens, as if some hidden cosmic hand starts feeding extra high-energy particles into the mix. Theories about what causes this spectral kink read like a debate among cosmic detectives. One camp argues it's a signpost for where galactic cosmic rays, those born within our Milky Way, lose dominance to their extragalactic cousins. Imagine a stream merging into a river. The ankle might mark the point where local particle sources get drowned out by far more powerful accelerators from distant galaxies. Supporting this idea, the ankle's energy aligns roughly with calculations of how far protons can travel before the Milky Way's magnetic fields drain their momentum. Beyond this point, only particles forged in truly cataclysmic intergalactic events like quasars or colliding galaxy clusters would have enough residual energy to reach Earth. But alternative explanations twist this narrative. Some models suggest the ankle represents not a source transition, but a change in how cosmic rays lose energy during their journey. At lower energies, particles interact strongly with interstellar gas, shedding momentum like cars braking in traffic. Above the ankle's threshold, they might slip through these obstacles more easily, like motorcycles weaving between gridlocked vehicles. Others propose it's evidence of exotic physics, perhaps cosmic rays interacting with dark matter or even decaying super-heavy particles left over from the Big Bang. The puzzle deepens when you examine the ankle's shape up close. Detailed measurements from observatories like the telescope array reveal it's not a sharp corner but a smoothed curve, suggesting overlapping processes rather than a single switch. Some researchers even spot hints of a second, subtler bend above the ankle, dubbed the toe, where the spectrum might transition again to particles from entirely different cosmic accelerators. It's as if the universe has multiple gears for particle acceleration, each kicking in at different energy thresholds. What makes the ankle so valuable is its universality. Every time we measure cosmic rays, whether with balloons in the stratosphere, detectors on mountain peaks, or instruments in space, this feature reappears with eerie consistency. That reliability makes it a Rosetta Stone for decoding cosmic ray origins, offering clues about both the particles' birthplaces and the environments they traverse to reach us. Yet, like any good cipher, it refuses to yield easy answers, challenging each new generation of physicists to peel back another layer of cosmic mystery. The ankle's persistence across decades of data collection speaks to something fundamental about how the universe organizes its particle accelerators. Whether it's marking a boundary between galactic and extragalactic realms, revealing unseen energy loss mechanisms, or hinting at new physics, this unassuming kink in a graph may hold keys to understanding nature's most powerful engines. And with next-generation detectors coming online, we might finally be on the verge of reading the full message hidden in this cosmic cipher. Among the most compelling evidence that supernovas serve as cosmic particle accelerators comes from a ghostly ring of energy in the constellation Cygnus. Astronomers studying the aftermath of a star that exploded roughly 8,000 years ago found something extraordinary. The shockwave from that ancient detonation is still pulsing with high-energy protons, electrons, and other particles moving fast enough to qualify as cosmic rays. This supernova remnant, known as the Cygnus loop, acts like a natural laboratory, demonstrating how stellar explosions can energize matter to relativistic speeds through processes we're only beginning to understand. At the heart of this phenomenon lies a mechanism called diffusive shock acceleration. When a star goes supernova, it blasts material outward at thousands of kilometers per second, creating a shock front that plows through surrounding interstellar gas like a snowplow through powder. Particles caught in this turbulent boundary don't just get pushed along, they become trapped between the advancing shockwave and magnetic fields tangled in its wake. Each time these particles cross the shock front, they gain energy, bouncing back and forth like rubber balls between moving walls. Over centuries, what began as sluggish protons or electrons transform into high-velocity projectiles, eventually breaking free to streak across the galaxy as bona fide cosmic rays. X-ray and gamma-ray observations provide smoking gun evidence for this process. The Fermi Gamma-Ray Space Telescope has detected characteristic signatures of pion decay near several supernova remnants telltale gamma rays produced when accelerated protons collide with interstellar gas, creating unstable particles that almost immediately break down into energy. It's the cosmic equivalent of finding gunpowder residue at a crime scene. Even more convincing are measurements showing enhanced cosmic ray densities precisely where supernova shockwaves interact with dense molecular clouds, confirming these regions act as natural particle boosters. What makes supernova remnants especially efficient cosmic ray factories is their longevity. While the initial explosion lasts mere weeks, the shockwaves can persist for tens of thousands of years, continuously pumping energy into particles. The Crab Nebula, the remnant of a supernova observed in 1054, still emits particles with energies up to 1,000 trillion electron volts, detectable through the eerie blue glow of its synchrotron radiation. Modern estimates suggest a single supernova remnant can convert up to 10% of its explosion energy into cosmic rays, making these stellar graveyards some of the most prolific particle accelerators in the galaxy. Yet mysteries remain. Recent observations of the Tycho supernova remnant revealed cosmic rays with unexpectedly sharp energy cutoffs, suggesting our models of shock acceleration may be incomplete. Some theorists now propose that turbulent magnetic fields near supernova shocks create accelerator within an accelerator, affects localized zones where particles get supercharged beyond standard predictions. Others speculate that the most extreme cosmic rays might require multiple supernova shocks acting in sequence, with particles gaining incremental boosts from successive stellar explosions as they traverse the galaxy. The implications stretch far beyond astrophysics. If supernovas truly are the primary source of galactic cosmic rays, their distribution should mirror the locations of recent stellar explosions, a pattern astronomers are actively mapping. Intriguingly, the local bubble, a cavern of relatively empty space surrounding our solar system, was likely carved out by a series of supernovas that detonated millions of years ago. The cosmic rays we detect today might be lingering echoes of those ancient cataclysms, their journeys through interstellar space finally ending in the glow of our detectors after eons of travel. As observatories like the Cherenkov Telescope Array come online, capable of imaging supernova remnants with unprecedented gamma-ray resolution, we're poised to unlock new secrets about these natural particle accelerators. Each measurement brings us closer to understanding how the violent death throes of stars seed the galaxy with high-energy particles that may have played crucial roles in shaping everything from Earth's radiation environment to the chemical building blocks of life itself. The universe glows with light stars, galaxies, and the cosmic microwave background painting the heavens in a tapestry of radiation. But hidden within this luminous sea is something far more energetic, cosmic rays that collectively carry more raw power than all starlight combined. It's a staggering imbalance. While photons from stars bathe the cosmos in gentle illumination, these high-speed particles pack enough punch to outshine every other radiation source in the universe combined. Consider the numbers. The total energy density of starlight across the observable universe amounts to roughly 1 electron volt per cubic centimeter, about as much energy as a single flying mosquito. Cosmic rays, by contrast, boast an energy density 10 times higher, with the most extreme particles delivering millions of times more energy individually than even the hottest stars emit per photon. Imagine comparing the glow of a nightlight to the concentrated blast of a particle accelerator. That's the scale difference between cosmic rays and starlight. What makes this energy dominance so astonishing is its stealth. Unlike starlight, which we see with our eyes and telescopes, cosmic rays pass through most detection methods unnoticed unless captured by specialized equipment. Their energy isn't radiated smoothly like a star's warmth. It's delivered in violent, concentrated packets, subatomic bullets carrying kinetic energy that can rival macroscopic objects. A single ultra-high-energy cosmic ray might deposit as much energy in a detector as several hundred visible light photons combined, despite being just one particle among trillions. This energy asymmetry reshapes our understanding of cosmic ecosystems. In galaxy clusters where hot gas emits copious X-rays, cosmic rays likely contribute comparable energy to the system's total budget, not as diffuse heat, but as discrete, high-velocity particles stirring the interstellar medium like invisible whisks. Their collisions with gas atoms can trigger secondary reactions that produce gamma rays, neutrinos, and even rare isotopes, effectively seeding the universe with nuclear byproducts starlight alone could never create. The sources of this particle powerhouse are equally mind-bending. While stars generate light through relatively sedate nuclear fusion, cosmic rays are born from chaos supernova shockwaves, black hole jets, and other processes where magnetic fields twist spacetime itself into natural accelerators. It's the difference between a campfire's steady glow and the instantaneous flash of a lightning bolt. Both release energy, but one does so with blistering intensity. Yet for all their might, cosmic rays remain curiously fragile messengers. Their charged nature means they're easily deflected by magnetic fields, scrambling directional clues about their origins. While starlight travels straight from source to observer over billions of years, cosmic rays zigzag unpredictably, their paths twisted into near unrecognizability. This irony defines their study. The universe's most energetic particles are also some of its most elusive, their power unmatched but their stories frustratingly scrambled by the cosmos itself. Measuring this particle dominance requires ingenious techniques. Astronomers use gamma-ray telescopes as cosmic ray proxies, since many high-energy photons arise directly from cosmic ray interactions. Others track synchrotron radiation, the eerie glow emitted when relativistic electrons spiral through magnetic fields, to map where these particles concentrate. The data reveals a universe far more dynamic than light alone suggests, with particle energy rivaling or exceeding electromagnetic radiation in regions from supernova remnants to active galactic nuclei. This hidden energy reservoir has profound implications. Some theories suggest cosmic rays play pivotal roles in star formation, their ionizing radiation helping collapse gas clouds into protostars. Others posit they influence galactic weather, driving winds that shape entire galaxies over eons. Even Earth's climate may feel their subtle touch, with some research linking cosmic ray flux to atmospheric ionization and cloud formation. While starlight illuminates the universe, cosmic rays seem to sculpt it, their invisible hands shaping structures from the smallest molecular clouds to the largest galactic filaments. The next time you gaze at the night sky, remember, what you see is just the surface. Behind every twinkling star lies a deeper, more violent cosmos, one where particles too small to see carry energies too large to ignore, quietly dominating the universe's energy budget while remaining invisible to the naked eye. It's a humbling reminder that sometimes the most powerful forces come packaged in the smallest things. Attached to the International Space Station like a high-tech barnacle, the Alpha Magnetic Spectrometer represents humanity's most sophisticated attempt to catch cosmic rays in the act of revealing one of the universe's deepest secrets, antimatter. This $2 billion physics experiment, about the size of a small school bus, has been silently sifting through billions of cosmic particles since its installation in 2011, hunting for traces of antimatter that could rewrite our understanding of cosmic origins. Unlike ground-based detectors that only see the debris from atmospheric collisions, AMS-02 intercepts pristine particles before Earth's air can alter them, giving scientists an unprecedented view of the cosmos's raw ingredients. The spectrometer operates like a cosmic sorting machine, using powerful magnets and ultra-sensitive detectors to measure each particle's charge, velocity, and mass as it zips through. But the real prize lies in spotting particles that shouldn't exist: antihelium nuclei, or heavier antimatter atoms that might have survived from the Big Bang. According to standard physics, antimatter should have completely annihilated with matter shortly after the universe's birth, leaving behind only the slight matter excess we're made of today. Finding even a single antihelium nucleus in cosmic rays would suggest entire regions of antimatter survived this ancient annihilation. Perhaps even whole antistars or antigalaxies lurking in the cosmic darkness. AMS-02 precision borders on the miraculous. Its silicon trackers can resolve particle paths to within 10 microns, about a tenth the width of a human hair, while its ring imaging Cherenkov detector measures velocity to within a mind-boggling 1 part in 10,000. This lets it distinguish between regular helium nuclei and their antimatter twins with near-perfect accuracy. The detector has already catalogued over 200 billion cosmic ray events, creating a particle census that's reshaping astrophysics. Among its surprises were unexpected fluctuations in positron fractions at certain energies, hints of possible dark matter annihilations or undiscovered astrophysical phenomena. The experiment's endurance is as remarkable as its technology. Originally designed for a 3-year mission, AMS-02 has far outlasted expectations despite facing extreme temperature swings between sunlight and shadow every 45 minutes as the ISS orbits Earth. NASA even conducted a series of unprecedented spacewalks to repair the spectrometer's failing cooling pumps in 2019 and 2020, extending its lifespan into the 2030s. This longevity has allowed AMS-02 to detect rare high-energy particles that might only arrive once every few months, gradually building statistical certainty where other experiments see only noise. What makes the antimatter search so compelling is its potential to answer one of cosmology's biggest questions: why does anything exist at all? The Big Bang should have created equal amounts of matter and antimatter, which would have annihilated completely. That we're here proves some tiny asymmetry favored matter, but no known physics explains this imbalance. AMS-02 might spot clues in the energy spectra of antiprotons or positrons, deviations from predictions that could point to exotic processes in the early universe. Some theories suggest dark matter particles colliding in space could produce antimatter signatures detectable by the spectrometer, offering 2 cosmic mysteries for the price of one. The experiment's location on the ISS isn't just practical, it's poetic. As astronauts float through the station's modules, separated from the void by mere centimeters of metal, AMS-02 silently monitors the same space environment that could conceal answers to existence itself. Every particle it analyzes has journeyed across light years, carrying encrypted messages about the universe's most violent events and fundamental symmetries. While the antimatter hunt continues, the spectrometer has already transformed cosmic ray science, proving that sometimes the best way to study the universe's grandest questions is to catch its smallest fragments in the act of whispering their secrets. High above storm clouds, where the atmosphere thins to near vacuum, cosmic rays may play puppet master to one of nature's most dramatic displays: lightning. For decades, scientists assumed thunderstorms generated their own sparks through simple charge separation within clouds. But emerging research suggests these terrestrial fireworks might need an extraterrestrial kickstart, with high-energy particles from deep space acting as invisible matchsticks in Earth's atmospheric tinderbox. The chain reaction begins when a cosmic ray, often a proton moving at nearly light speed, plows into the upper atmosphere. This collision shatters air molecules, creating a shower of secondary particles, including electrons stripped from atoms. These free electrons become the seeds for runaway breakdown, a cascade effect where each accelerated electron ionizes more molecules, multiplying their numbers exponentially. Within milliseconds, what began as a single particle impact blossoms into a conductive plasma channel, a microscopic highway of charged particles threading through the storm cloud's electric field. Here's where the magic happens. Normally, air acts as an insulator, preventing electricity from flowing freely. But these cosmic ray-induced plasma trails provide the perfect conductive pathway for lightning's initial leader stroke. The faint precursor that carves the ionized path a visible bolt will follow. Satellite observations have captured gamma-ray flashes from thunderstorms aligning suspiciously with cosmic ray air showers, while ground-based radio detectors note spikes in particle activity moments before lightning strikes. It's as if the sky waits for a cosmic nudge before unleashing its pent-up energy. The theory gained traction after a startling discovery: lightning doesn't always strike from cloud to ground. Some bolts fire upward, starting near the storm's top and shooting toward space. These gigantic jets and sprites occur at altitudes where cosmic rays are most active, with particle detectors recording surges during such events. Laboratory experiments using particle accelerators to simulate cosmic rays have successfully triggered electrical discharges in artificial thunderclouds, lending credence to the idea that space particles help bridge the gap between atmospheric charge separation and full-blown lightning. But the plot thickens when you consider global patterns. Lightning frequency fluctuates with the solar cycle, dipping when the sun's magnetic field strengthens and deflects more cosmic rays away from Earth. Intriguingly, some studies suggest lightning rates may have dropped slightly during the 20th century rise in air pollution, as aerosols absorbed the ionization energy that cosmic rays typically provide. This delicate interplay between extraterrestrial particles and terrestrial weather hints at a universe far more interconnected than we once imagined. Not all physicists are convinced. Critics point out that while cosmic rays undoubtedly ionize air, thunderstorms generate such enormous voltages that they shouldn't need outside help to spark. Alternative models propose that ice crystal collisions or turbulent winds within clouds create sufficient ionization naturally. Yet the sheer timing coincidence between particle showers and lightning initiation keeps the debate alive, with newer detectors like the Lightning Mapping Array providing increasingly precise data on how discharges begin. Whether cosmic rays are essential triggers or merely opportunistic enhancers, their potential role rewrites lightning's origin story from a purely terrestrial phenomenon to a cosmic collaboration. Next time you see a bolt split the sky, consider this. That brilliant flash might have begun with a particle from a supernova thousands of light years away, its journey culminating not in the cold void of space, but in the explosive meeting of cloud and ground, proof that even Earth's most familiar forces can have unexpectedly stellar origins. Dark matter remains one of the universe's most frustrating enigmas, an invisible substance that outweighs normal matter 5 to 1, yet refuses to show itself except through gravitational tugs on galaxies. But cosmic rays might finally be lifting the veil on this cosmic ghost, carrying subtle fingerprints of dark matter's existence in their energy signatures. The key lies in what physicists call indirect detection. Rather than spotting dark matter directly, we look for the debris it leaves behind when colliding or decaying in space. And nothing delivers that debris more clearly than the high-energy particles raining down from the cosmos. The search centers on puzzling anomalies in cosmic ray data. When satellites like the Alpha Magnetic Spectrometer and ground-based detectors tally up certain particles, especially positrons and antiprotons, they find more at specific energy ranges than standard astrophysics predicts. These excesses form unexpected bumps in graphs where smooth curves should be, like finding extra stair steps in a familiar flight. One compelling explanation: collisions between dark matter particles in our galactic halo. According to many theories, when these invisible particles annihilate or decay, they should produce showers of familiar particles we can detect, including the very cosmic ray anomalies puzzling scientists. The most tantalizing clue came in 2008, when the Pamela satellite detected a dramatic rise in positron fractions at energies around 10 gigaelectronvolts, a surge that ballooned with energy instead of tapering off as expected. Later confirmed by MS-02 on the ISS, this anomaly matched predictions for certain dark matter models, particularly weakly interacting massive particles WIMP with masses around 1 teraelectronvolt. Imagine dark matter as two invisible wrecking balls smashing together in deep space, their collision spraying out positrons like sparks from a grindstone. Cosmic rays act as the spark collectors, bringing those telltale fragments to our detectors, but the cosmic ray dark matter connection runs deeper than positron excesses. Some models predict dark matter could produce sharp gamma-ray lines in cosmic ray spectra, distinct energy spikes like fingerprints left at a crime scene. Others suggest looking for anti-deuterons, rare antimatter nuclei that will be smoking guns for dark matter interactions, since they're seldom produced by ordinary astrophysical processes. The challenge lies in distinguishing dark matter signals from cosmic ray background noise, the constant drizzle of particles from pulsars, supernova, and other conventional sources. It's like trying to hear a whisper at a rock concert. You need exquisitely sensitive instruments and clever filtering techniques. Recent advances are turning the tide. The DAMP satellite's 2017 detection of a positron/electron flux break at 1 teraelectronvolt provided the first hint of a possible cutoff energy, exactly what some dark matter models predict. Meanwhile, experiments like CTA, the Cherenkov Telescope Array, are hunting for gamma-ray signatures from dwarf galaxies where dark matter should cluster densely. Even neutrino telescopes join the chase, since high-energy neutrinos could be byproducts of dark matter decays in the Sun's core, where gravity has concentrated these elusive particles. The implications of a cosmic ray dark matter link would reshape physics. Confirming dark matter's particle nature could unlock mysteries from galaxy formation to the universe's ultimate fate. It might even reveal connections to extra dimensions or supersymmetry theoretical frameworks where every known particle has a heavier, dark matter counterpart. Until then, cosmic rays remain our most promising messengers from the dark sector, high-energy postcards from an invisible universe waiting to be decoded. Perched 4,300 meters above sea level on the Tibetan Plateau, the world's highest cosmic ray lab stares into the thin mountain air, waiting for the invisible shrapnel of distant stellar explosions. The Tibet Air Shower Array isn't your typical observatory. It has no domes or telescopes. Instead, its detectors sprawl across 65,000 square meters of rugged terrain, an interconnected web of sensors designed to catch the aftermath of cosmic rays colliding with Earth's atmosphere. At this altitude, where the air is 40% thinner than at sea level, the array gets front-row seats to particle cascades before too much atmosphere interferes. The secret to its success lies in repurposing the sky itself as a detection medium. When an ultra-high-energy cosmic ray slams into the atmosphere, it triggers an avalanche of secondary particles, muons, electrons, gamma rays that fan out across kilometers. The Tibet Array's grids of plastic scintillators and underground muon detectors act like a giant cosmic net, measuring the intensity and spread of these particle showers to reconstruct the original cosmic ray's energy and direction. It's akin to determining the size and speed of a meteor by studying the splash pattern of its fragments in a pond. What makes this high-altitude setup revolutionary is its hybrid approach. Unlike detectors at sea level that see only the surviving remnants of air showers, the Tibet Array catches cascades mid-development. Its elevation allows precise measurement of the shower's core, the dense central region where most particles cluster, revealing whether the primary cosmic ray was a lightweight proton or a heavier atomic nucleus like iron. This distinction is crucial as heavier nuclei suggest different acceleration mechanisms and cosmic origins. The array's location isn't just about altitude, it's a strategic cosmic sweet spot. Sitting near Earth's geomagnetic equator, it receives a more uniform distribution of cosmic rays from all directions compared to polar installations, where Earth's magnetic field funnels particles unevenly. Over 3 decades of operation, it's catalogued millions of events, including ultra-high-energy gamma rays that might trace back to pulsars or supernova remnants. One of its landmark discoveries came in 2021, when it detected gamma rays with energies surpassing 1 peta-electronvolt, 1,000 trillion electronvolts originating from the Crab Nebula. These photons, propelled by the nebula's spinning neutron star, demonstrated nature's ability to accelerate particles to energies 100 times greater than the Large Hadron Collider. The find confirmed supernova remnants as cosmic ray factories, while raising new questions about how their turbulent magnetic fields achieve such extremes. Maintaining this scientific outpost is a feat of endurance. Technicians brave sub-zero temperatures and oxygen-thin air to calibrate detectors, while custom electronics withstand intense ultraviolet radiation at this elevation. Yet the harsh environment pays dividends. The thin, dry atmosphere minimizes water vapor interference, letting the array spot subtle differences in particle showers that low-altitude detectors might miss. As upgrades install next-generation muon detectors and tighter sensor spacing, the Tibet Array is poised to tackle cosmic ray mysteries that require immense statistics, like hunting for ultra-rare gamma rays from dark matter annihilation or probing the disputed Ni region of the cosmic ray spectrum where particle origins may shift from galactic to extragalactic. Every storm of particles it records carries encrypted messages about the universe's most violent engines, decoded by a silent sentinel standing where Earth's atmosphere meets the void. From comic books to blockbuster films, cosmic rays have powered some of fiction's most iconic transformations, bending the laws of physics to suit the needs of storytelling. Take Marvel's Fantastic Four, whose origin story hinges on a fateful encounter with cosmic radiation during a scientific mission in space. Exposed to these high-energy particles, Reed Richards gains elasticity, Sue Storm turns invisible, Johnny Storm bursts into flames, and Ben Grimm transforms into the rock-skin thing. While real cosmic rays would more likely give astronauts radiation sickness than superpowers, the comic's pseudoscientific explanation tapped into genuine public fascination with these mysterious particles, especially during the 1960s space race when cosmic rays were front-page news. Hollywood has taken even greater liberties, often portraying cosmic rays as glowing energy beams or colorful intergalactic storms. In The Core, a 2003 disaster film, cosmic rays threaten to microwave Earth's surface after the planet's magnetic field collapses, an absurd premise that conflates cosmic rays with microwave radiation. Yet the film's exaggerated scenario isn't entirely baseless. Earth's magnetic field does deflect lower-energy cosmic rays, and without it, surface radiation would indeed increase, albeit not at apocalyptic speeds. Similarly, Lucy, starring Scarlett Johansson, suggests cosmic rays might unlock untapped brain potential, a trope that echoes mid-century fears and fantasies about radiation's effects on human evolution. These fictional portrayals often reflect their era's scientific anxieties. Cold War-era comics like The Incredible Hulk tied gamma-ray exposure to monstrous transformations, mirroring societal fears of nuclear fallout. More recently, Stranger Things wove cosmic rays into its 1980s-inspired lore, with the upside-down gates opening after Hawkins' National Laboratory experiments with high-energy particles. Even video games like Fallout use cosmic radiation as a handwave for mutations, blending real science with speculative fiction, yet some stories come surprisingly close to reality. Arrival 2016 features linguists decoding an alien language linked to cosmic ray exposure, a nod to how interstellar particles might carry information across galaxies. Contact, based on Carl Sagan's novel, depicts cosmic rays as potential carriers of extraterrestrial messages, an idea actual scientists have explored through projects like the Search for Extraterrestrial Intelligence. The 2022 film Moonfall took this further, suggesting cosmic rays could trigger lunar upheavals, a fantastical twist on real concerns about space weather's impact on technology. What makes these fictional portrayals compelling isn't their accuracy, but how they repackage cosmic wonder into relatable narratives. Whether it's Godzilla's atomic breath or Spider-Man's radioactive spider bite, pop culture has turned cosmic rays into shorthand for transformation, both terrifying and miraculous. Behind every exaggerated Hollywood beam lies a kernel of truth. These invisible particles from deep space really do rewrite matter at the atomic level, even if their real-world effects are less flashy than a superhero's origin story. The next time you see a character bathed in cosmic energy, remember the actual science is wild enough, with particles crossing galaxies to leave their mark on everything from our atmosphere to our DNA. Every second, Earth's upper atmosphere becomes the bullseye in an invisible cosmic shooting gallery, hit by around 5,000 cosmic rays per square meter. That's not just a light drizzle, it's a relentless downpour of high-energy particles, each one a splinter of distant stellar violence finding its way to our doorstep. Picture this: over the course of a single day, your backyard alone gets strafed by more than 400 million of these subatomic bullets, all traveling near light speed after journeys spanning millions of light years. But here's where the numbers get staggering. When you scale up to the entire planet's surface, Earth absorbs roughly 100 quadrillion cosmic ray impacts every single second. That's a 1 followed by 17 zeros, a figure so large it rivals the number of grains of sand on all the world's beaches combined. And this isn't some occasional cosmic storm. It's a constant bombardment that's persisted for billions of years, etching its influence into everything from our atmosphere's chemistry to the very mutations driving evolution. These particles arrive in layers like an inverted rainstorm. At the top of the atmosphere, primary cosmic rays, mostly protons, collide with nitrogen and oxygen atoms, shattering them into secondary particles, muons, pions, electrons, and gamma rays. By the time this cascade reaches sea level, it's transformed into a diffuse shower with roughly 1 muon passing through your hand every second. Even deep underground, in tunnels and caverns shielded by kilometers of rock, sensitive detectors still catch the occasional muon that tunneled through the planet's bulk like a ghost slipping through walls. The bombardment fluctuates with subtle rhythms. During solar maximum, when the sun's magnetic field is strongest, cosmic ray flux drops by about 20% as our star's enhanced magnetism deflects lower energy particles away from Earth. Airline passengers experience this variability firsthand. A flight from New York to London during solar minimum exposes travelers to double the cosmic radiation dose of the same trip during solar maximum. Even Earth's own magnetic field shapes the onslaught, funneling more particles toward the poles while shielding equatorial regions. A phenomenon visible in the heightened radiation levels astronauts encounter when crossing the South Atlantic anomaly, where our planet's magnetic shield weakens. What's truly humbling is how this perpetual particle storm links us to the wider cosmos. Every square centimeter of your body gets hit by a cosmic ray muon about once a minute, meaning, as you watch this sentence, particles from exploded stars and active galaxies are stitching their way through your cells. Some theorists speculate this steady irradiation may have played a role in life's earliest genetic mutations, subtly steering evolution's course over eons. From shaping clouds to triggering lightning, from leaving traces in ancient rocks to peppering our DNA with delicate damage, cosmic rays are the universe's way of reminding us we're not isolated observers of the cosmos, but active participants in its endless particle conversation. The next leap in cosmic ray science won't come from bigger detectors, but from smarter ones. Enter the Cherenkov Telescope Array, or CTA, a revolutionary observatory designed to catch the universe's most energetic particles in ways previous instruments couldn't even imagine. Spread across two hemispheres, with one site in Chile's Atacama Desert and another on Spain's Canary Islands, this network of over 100 telescopes represents a quantum leap in precision, capable of spotting cosmic ray-induced air showers with resolutions sharp enough to distinguish individual particle types by their faint blue Cherenkov glow. Unlike traditional arrays that focus on counting particles, CTA's innovation lies in its hyperspectral approach. Each telescope tier targets different energy ranges. Small telescopes catch ultra-high energy showers, medium ones track moderate events, and massive 23-meter dishes zero in on the faintest signals. This layered system acts like a cosmic ray prism, breaking particle showers into their component wavelengths much like light through a spectroscope. The result: unprecedented ability to determine whether a shower was triggered by a proton, ion nucleus, or even a gamma-ray photon, crucial clues for tracing particles back to their birthplaces. What truly sets CTA apart is its timing precision, able to sync telescope signals to within 1 nanosecond. This lets it reconstruct shower development with frame-by-frame accuracy, mapping how particle cascades evolve millisecond by millisecond. Imagine reconstructing a meteor's path not from its burnt remnants, but by photographing every millisecond of its atmospheric disintegration. That's the level of detail CTA brings to cosmic rays. The array's expected sensitivity will detect sources 10 times fainter than current telescopes, potentially revealing cosmic ray factories we didn't know existed. One of CTA's most anticipated targets is the elusive P-Vatron class of accelerators, cosmic engines capable of pushing particles to petaelectronvolt energies. While supernova remnants were long thought to reach these extremes, no existing telescope has definitively caught them in the act. CTA's ability to pinpoint gamma-ray signatures from pion decay could finally provide smoking gun evidence, settling decades-old debates about where our galaxy's most powerful particles get their kick. The observatory's design also tackles cosmic rays' directional ambiguity problem. By combining its particle tracking with gravitational wave and neutrino data, CTA will perform multi-messenger triangulation, essentially cross-referencing cosmic ray arrivals with other cosmic signals to pinpoint origins. This collaborative approach might finally crack the mystery of whether ultra-high-energy particles come from active galactic nuclei, neutron star mergers, or something even more exotic lurking in the voids between galaxies. Scheduled for full operation by 2030, CTA won't just observe cosmic rays, it will profile them with forensic detail, analyzing each particle's energy spectrum, composition, and arrival direction like a detective scrutinizing evidence. Future upgrades could link it to space-based detectors like the proposed POMA mission, creating an interplanetary cosmic ray monitoring network. Together, these next-generation instruments will transform how we see and understand the invisible particle storm that's been bombarding Earth since long before life began. For all we've uncovered about cosmic rays, their most profound secrets remain locked away, puzzles so baffling they redefine what we thought possible. At the top of the list looms the trans-GZK conundrum, particles arriving with energies that should be impossible under current physics. The Greisen-Zatseping Kuzmin cutoff clearly predicts protons above a certain energy can't travel far without losing momentum to cosmic microwave background photons. Yet detectors keep catching these rule breakers, some with energies equivalent to a well-thrown baseball crammed into a single proton, where do they come from? Either there's an undiscovered population of hyper-efficient accelerators lurking nearby in cosmic terms, or our understanding of particle interactions at extreme energies contains fundamental flaws. Equally perplexing is the composition mystery. While most cosmic rays are protons, the highest energy events appear to be heavier nuclei like iron, a finding that upended decades of assumptions. If true, this suggests unimaginable cosmic furnaces capable of stripping atoms bare and launching their nuclei across galaxies without reducing them to subatomic debris. The required conditions defy even our most extreme astrophysical models, pointing to acceleration mechanisms we've yet to imagine. Some theorists speculate these heavy cosmic bullets might originate from quark nova explosions, hypothetical stellar implosions even more violent than supernovas, or from the disintegration of primordial cosmic strings left over from the Big Bang. Then there's the directional puzzle. Despite building continent-sized detector arrays, we still can't reliably trace ultra-high-energy cosmic rays back to their sources. Galactic magnetic fields twist their paths into indecipherable knots, while the particle's extreme rarity makes statistical analysis fraught. The few tentative correlations, like hotspots near active galaxy Centaurus A, only deepen the mystery. Why do some regions produce excess particles while seemingly identical cosmic environments don't? The answer might involve hidden variables in galaxy evolution or large-scale magnetic field structures we've yet to map. Perhaps most tantalizing are the theoretical wildcards. Some models suggest certain cosmic rays could be relic particles from the early universe, frozen remnants of physics operating at energies unreachable since inflation ended. Others propose their signatures of dark matter annihilation or decay, with their energy spectra holding clues to that elusive substance's true nature. There's even speculation that a handful might originate from entirely new astrophysical phenomena, collisions between theoretical objects like cue balls or magnetic monopoles that could rewrite particle physics. The detection challenges themselves pose another layer of mystery. Current observatories catch maybe one ultra-high-energy cosmic ray per square kilometer per century. Next-generation detectors like the proposed giant radio array for neutrino detection, GRAND, aim to cover millions of square kilometers using radio antennas to track atmospheric showers, but even this may not provide the statistical heft needed for definitive answers. We're essentially trying to reconstruct a cosmic crime scene with just a few scattered fingerprints and no witnesses. Underlying all these questions is a deeper philosophical quandary. Are we seeing the limits of known physics or merely the limits of our imagination? Every anomalous cosmic ray carries encrypted information about the universe's most extreme environments, black holes spinning at relativistic speeds, shocks waves spanning galactic clusters, or perhaps phenomena we haven't yet conceived. As astronomer Carl Sagan once noted, extraordinary claims require extraordinary evidence, but cosmic rays keep delivering evidence that demands we reconsider what's truly extraordinary in our universe. The coming decades promise transformational insights as neutrino observatories, gravitational wave detectors, and cosmic ray telescopes begin working in concert. Like detectives comparing notes across jurisdictions, these multi-messenger approaches may finally crack cases single instruments couldn't solve alone. Until then, each high-energy particle that streaks through our atmosphere carries both a challenge and an invitation to look deeper, think broader, and embrace the beautiful uncertainty at the frontier of cosmic discovery. From the oh my god particle's impossible energy to cosmic rays sparking lightning on Earth, we've traveled through a universe far stranger than fiction. These invisible messengers have rewritten the rules of physics, exposed our planet to a constant subatomic storm, and even left their fingerprints inside your DNA. Yet for every mystery solved, two new ones emerge, like why some particles arrive with energies that defy all known limits, or whether dark matter is whispering through their detection patterns. Think about this. Right now, as you watch this, particles from exploded stars are passing through your body after journeys spanning millions of years. Some may have been forged in black hole jets or supernova shockwaves so powerful they make hydrogen bombs look like firecrackers. Others could carry clues about antimatter galaxies or cosmic strings, relics from the universe's birth. And despite centuries of study, we've barely scratched the surface. The highest energy cosmic rays remain cosmic riddles, their origins hidden in the magnetic tangles of intergalactic space. This isn't just science, it's the ultimate detective story. Every detection is a breadcrumb leading toward understanding how the universe concentrates energy, how matter behaves at its limits, and what invisible forces shape the cosmos. The answers won't just satisfy curiosity, they could revolutionize everything from energy technology to space travel. So stay curious. The next cosmic ray could carry the clue that changes everything, and you'll find those breakthroughs right here. Subscribe now to explore more mysteries of the universe, from the particles smaller than atoms to the galaxies larger than imagination. The cosmos is speaking. All we have to do is